Today we're going to do a couple quick examples of inverting exponential and logarithmic functions. So our first example is f of x. F of x equals 5 times 2 to the power of x minus 2. And we are going to invert this function. And the first step is always to replace that f of x with y, and then carry down the remainder of our formula or equation. And then we switch our x and y values. So we now have x equals 5 times 2 to the power of y minus 2. But here's a problem. If we're going to solve for y, we have to be able to get y out of the exponent. And this means we're going to need to use our power of logarithms. So first, let's get 2 to the power of y by itself. We can do that in 2 steps by adding 2. So we have x plus 2. And then we're going to also divide by 5. And now we convert this to exponential form, or excuse me, logarithmic form, because we're inverting an exponential equation. So I'm going to have logarithm base 2 of what's on the left side. So that's x plus 2 all divided by 5 is equal to y. But I don't want to call it y, so instead I'm going to call it f inverse of x is equal to the logarithm base 2 of x plus 2 all divided by 5. And this is our inverse for the function f of x equals 5 times 2 to the power of x minus 2. So let's really quickly just show how we might verify this. And let's plug our inverse into our original function. So we have f composed with f inverse. And so this is going to be 5 times 2, but I have to put this whole thing as an exponent. So log base 2 of x plus 2 all divided by 5, and then we're subtracting 2. So we have to remember our properties of logarithms. When we have 2 to the power of log base 2, those cancel out. So this 2 and that whole expression go away, and we're just left with 5 times x plus 2 over 5 minus 2. The 5's cancel out. We have x plus 2 minus 2. The 2's cancel out, and we're left with x. Now again, if we were to be ideal and rigorous, we would show this is true in both directions. But to keep the video shorter, we're just going to show the one direction. So let me erase this example, and then we'll work through an example of inverting g of x. So this function has our natural logarithm. And it's important to remember that our natural logarithm has base e. So we have base e. Base e, the number e is sort of like pi in that it's an irrational number that goes on forever. It's approximately equal to 2.718. So it's a little less than 3. It comes up in many interesting applications. But for now, our focus is inverting this function g of x. So first, let's do as we did before, replace g of x with y. And then we are going to switch the places of our x and y's. So we have x equals the natural log of 4 times y plus 3. And we're going to solve for y. So let's subtract 3 from both sides. So we have x minus 3 is equal to the natural logarithm of 4y. Now remember that I said the logarithm, the natural logarithm, has base e. So to help me convert this into exponential form, I'm going to replace that with log base e. Because if you remember from class, we can circle our base, spiral around, and this helps us know how to put it into exponential form. So we have e to the power of x minus 3 equals 4y. Now to solve for y, we divide everything by 4. So we have e to the x minus 3 all divided by 4. You can just barely still see that. There we go. And then we would call this g inverse of x. Notice that we're not calling it f inverse because our function started as g, and so we want to keep those names consistent. So let me erase our work for a moment so that we can show how we would verify this in the opposite direction. So I'm going to plug, same as before, our inverse into our original function. So we have the natural log of 4 times e to the power of x minus 3 over 4 plus 3. I think I'll probably need that space down there. So first things that happen, inside our logarithm, the 4's cancel out. So we're left with the natural log of e x minus 3 plus 3. Same as before. When we have an expression with the base inside the logarithm of the same base, these cancel out, and we're just left with the exponent x minus 3. And then what came after? Plus 3. Minus 3 plus 3 is 0. So we are yet again just left with x, verifying that these were in fact inverses. Most of the time, questions will ask us to find the inverse, but sometimes you'll be asked to verify that two functions, which you may not know if they're inverses, are inverses. If we can compose them and get x, our variable, then we can say they're inverses. If we get something other than x, they're not inverses. One thing to be very careful with is remembering our order of operations. I couldn't cancel the natural log in e until I had taken care of these 4's. That order of operations is really important when verifying inverses, so we don't make any reckless mistakes. So this has been a few examples of inverting logarithmic and exponential functions.